Okay. In this section, we're going to look at specific types of questions regarding computing the mean and variances, and that is linear combinations of random variables. And the reason why we're specifically looking at linear combinations is because there's some nice results. You can almost think of this as like a tips and tricks section, if you will, on making some of these computations easier than simply just using the definitions of computing the mean or the definition of computing the variance, using the appropriate expectation theorems, right? So what I mean by that is, if you go back and look at your notes, right, the variance and covariance, for example, of some random variables, we have these theorems. There's theorem 4.4, which is fine and handy, but I'm talking about like these original definitions of computing, maybe, you know, something like a variance there, if you will, or the expectation of some random variables, right? The mean of a function g of x using these theorems here. So in this section, we're going to look at specific cases of linear combinations, okay? So theorem 4.5 in our e-text, if a and b are constants, then the expected value of ax plus b is equal to a times the expected value of x plus b, which is kind of nice, especially if you already know the expected value of x. All right, and I'm going to go ahead and just work through a proof here. This works for any random variable x that's either continuous or discrete. And I'll just do a quick proof in the continuous case, just so we can see how this works. We don't do a lot of proofs in this course, but sometimes when they're relatively straightforward and maybe somewhat useful, it's nice to see. So let's just do a quick proof of showing that this is true here. Okay. How are we going to do that? We're just going to go ahead and use the definition of expected value. The expected value of ax plus b, according to the definition for the continuous case, would be the integral from minus infinity to infinity. Then we'd have ax plus b times our PDF f of x dx. All right, so what we can do here then is just a little bit of algebra. Let's distribute the f of x minus infinity to infinity. That's going to be ax times f of x, and then plus b times f of x dx. And what we can do now is use the addition rule or the summation rule for integration, the additive rule. This is equal to two separate integrals. The integral from minus infinity to infinity of ax times f of x dx plus the integral of b times f of x dx. And let's see, what else can we do here? On the first integral, we can, remember, a and b are constants, right? So we can factor out the a on the first integral. So that's going to leave us with a times x, or sorry, a times the integral of x times f of x dx. We can also factor out a b here. B times the integral from minus infinity to infinity of f of x dx. And now let's take a look at what we have. Right? Let's go ahead and just take a look at this. What do we have here? What's the integral? What's the integral from minus infinity to infinity of x times f of x dx? That is just, all of this is just by definition the expected value of x, right? The expected value of x, you integrate x times f of x dx. So that's a times the expected value of x then, and then b times, we have a times the expected value of x, so far good, and then b times, what is the integral from minus infinity to infinity of f of x dx? Well, provided f is a valid PDF, this has to integrate to 1. Right? One of the requirements of being a probability density function. So that's b times 1, which is just b. And that is exactly what we were looking for. That is exactly what we're looking for. Oop. Boom. There we go. All right. So, nice. That's nice. So let's apply this. Why is this beneficial? There's the proof. How do we use this theorem? How do we use Theorem 4.5? Let's take a look at this example. Let's go ahead and find the expected value of g of x, where g of x is equal to 4x plus 3. 4x plus 3 is a linear combination on x. So let's find that expected value with the PDF, continuous PDF x squared over 3, and x goes from -1 to 2. X goes from -1 to 2. Let's give this one a shot, shall we? All right, so according to the theorem, we want the expected value of g of x. So the expected value of 4x plus 3. That theorem says this is equal to 4 times the expected value of x plus 3. So all we need to do then is find the expected value of x. I believe we've already worked this example, but let's go ahead and just do this real quick for practice. We just need the expected value of x. So that's going to be equal to the integral. And in this case, our bounds go from -1 to 2. X times x squared over 3 dx. So I'll bring out that 1/3. Integrate from -1 to 2. X cubed dx. So that's going to be 1/3 times x to the 4th over 4. Plugging in our endpoints, being careful with our arithmetic, we should get 5/4 for the expected value of x. 5/4. So what is this equal to? What's the expected value of g of x then? This is 4 times 5/4 plus 3, which is 8. Bingo. That is 8. Awesome. There we go. So that's how we can apply that theorem. That's how we can apply that theorem. So that's kind of nice. Okay. What if you were asked to find the expected value of x squared plus x minus 2? This is not a linear combination on x, right? That is not of the form ax plus b. That is not a linear combination. So we cannot use that theorem, but there's something else we can use, right? We need another result. We would need to use another result, which I'll introduce right now. Theorem 4.6 in our area text says the expected value of g of x plus or minus h of x is equal to the expected value of g of x plus or minus the expected value of h of x. Okay. So what is this going to do for us here? This is very close to like the addition or subtraction rule for integration. In the sense that if I'm adding or subtracting functions of a random variable together, I can just look at the expectations of each of those individual functions and then add or subtract those expectations. Okay, so that's kind of nice. So in this case, if we were to take this example here now, if we were to do this and say, what about the expectation of x squared plus x minus 2? How do we apply this? Well, then this is going to be equal to, according to Theorem 4.6, this would be the expected value of, so in this case, we could say g of x would be like x squared plus the expected value, then h of x would be x minus 2, right? So we could split it up that way. There we go. We could even take this one step further, because x minus 2 is a linear combination of x, and so on that second term, we could apply Theorem 4.5. X minus 2 there would be expected value of x plus b, so this is going to be equal to, we have the expected value of x squared, plus, split this term up using Theorem 4.5, the expected value of x minus 2. expected value of x minus 2, right? And so based on the last example, we know that the expected value of x here is what, 5/4 minus 2. So what do we need then? We need the expected value of x squared. We need expected value of x squared. And so what is that going to be equal to? Expected value of x squared, we can do that integral real quick as well. Integrate from -1 to 2, x squared times x squared over 3 dx. Same PDF here, just continuing off of that last example. From -1 to 2, x squared over 3. And so this is 1/3 times the integral from -1 to 2, x to the 4th dx. So that is 1/3 times x to the 5th over 5, evaluated from -1 to 2. And running the endpoints through, I've got 33/15. 33/15 there. So then this is equal to 33/15 plus 5/4 minus 2, which is 1.45. 1.45. Okay, kind of nice. Kind of nice there. A few things that are worth mentioning here about Theorem 4.6. Okay, is that this extends to joint PDFs or random variables as well. I'm not going to go over every possible orientation of this, but I just want to mention this extends to joint PDFs and random variables as well. So if you want to see that in details, go ahead and check out Theorem 4.7 in the text if you want to see how that works out. Something that I want to also highlight to be careful with here, specifically what we've talked about so far, these are all about expectations. These are all about the mean of random variables or a function of a random variable. And you got to be careful when you're trying to look at applying these things that you're talking about the mean. Let's not assume that this is true for variances. And in fact, specifically, adding or subtracting functions for random variables drastically affects the variance there. So this is generally not true. Generally not true for, let's say, the variance of x plus y. Generally not true for like the variance of x plus y. You cannot split that up, right? That is not equal to, generally speaking, not equal to the variance of x plus the variance of y. That is generally not the case. It does typically work for expectation though, right? The expected value of x plus y would be equal to the expected value of x plus the expected value of y. That's essentially the introductory application of Theorem 4.7. Okay. All right. Cool. Good. I want to try to get through one more theorem here before we take a break. It looks like my pen is low on battery. So let's see if we can't finish this out. Theorem 4.8 says if x and y are independent, then the expected value of x times y. This is kind of a nice extension. So far we've got, think about this, just a linear combination on x, ax plus b. Then we've got something like, what about adding or subtracting functions on x? Now what about multiplying two things together, x times y? If they're independent, this is equal to the expected value of x times the expected value of y. If they're independent. If they are independent, have to be independent, then we get to use that. So that's kind of nice. So how does this help us out? Well, here's an example. Let's say we have the joint continuous PDF. Say x times 1 plus 3y squared over 4. So x goes between 0 and 2. Y goes between 0 and 1. And it's 0 otherwise. What are we going to do in this example? In this example, I want to go ahead and check that the expected value of x times y is equal to the expected value of x times the expected value of y, given that the expected value of x times y is equal to 5/6, given that the expected value of x times y is equal to 5/6, okay? And in order to save some effort here, I'm going to pull out some of the results that we already have about this joint PDF from section 3.4 here, okay? We saw in section 3.4, what are the marginals here? The marginals, if we go back to our notes and we take a look in chapter 3, 3.4, that's not it. Not there either. Boom, there we go. G of x is equal to x over 2. G of x is equal to x over 2 when x is between 0 and 2. And h of y is equal to 1 plus 3y squared over 2 there, okay? So we found that, those two marginals, so I'm going to copy those over to our new page in our notebook. I also want to mention that we noticed in that example that they were in fact independent, because the product of the marginals was equal to the PDF for all x and y. Okay, so we already know they are independent, but let me just go ahead and copy some of those things down. So what do we need here? I need g of x is x over 2. Back to chapter 4. Close this up. So the marginals were, what do we have here? Marginals are g of x equals x over 2. X is between 0 and 2. Normally this is not bad review to go ahead and try to compute those marginals. It's not something we want to forget. So we had that. The marginal for y, h of y, was equal to 1 plus 3y squared over 2. And that's for y between 0 and 1. Okay, so there's the marginals from our PDF. So we had those. And also noting that g of x times h of y is equal to f of xy for all x and y. Implied that we saw that these are independent. X and y are independent random variables. X and y are independent random variables, okay? Now, if they're independent then, right, Theorem 4.8 says, if they're independent, the expected value of x times y is equal to the expected value of x times the expected value of y. So we sort of know this theorem should work out. Let's just double check to make sure everything's kosher. So we have the left-hand side of our equation, expected value of x times y, is given to us as 5/6. So we need to verify that the right-hand side is also 5/6. If it is not, then something went wrong. Either we made a mistake in our calculus, or these are not actually independent random variables. Much more likely we made a mistake because we've checked the marginals, we think that they are, or we know that they are in fact independent. So let's go ahead and do the expected value of x here and the expected value of y integrations. Expected value of x, we're going to integrate from 0 to 2. Now, when you have a joint PDF to find the expected value of x, you're going to integrate the marginal. So we're going to integrate from 0 to 2, x times x over 2 dx, right? Because that's the marginal, g of x, goes from 0 to 2. So this is going to be 1/2 times the integral from 0 to 2 of x squared dx. I'll leave you to finish the details on the calculus. I have 4/3 for that. How about the expected value of y? Now we want to integrate y times the marginal with respect to y. So the marginal distribution of y would be 1 plus 3y squared over 2. Integrate with respect to y. Your bounds for y here go from 0 to 1. 0 to 1. And so this would be 1/2 times the integral from 0 to 1. And this is y plus 3y cubed after I distribute the y there. And we want to integrate that, except from 0 to 1. Again, I'll leave you to check the details there. I've got 5/8. Just trying to save some time because I've got a blinking red light on my new stylus, and I don't actually know how long that means I have. So there we go. There's our integration. This works out, so we just need to check our right-hand side then. Does it equal 5/6? 4/3 times 5/6 based on the application of this. Then is equal to 4 times 5 is 20, and then 18. 20 over 18 divided by 5/9. What the heck? That's not good. Oh, this isn't 5. This is 5/8. 5/8. Let's try again. 4 times 5 is 20. 3 times 8 is 24. Divide everything by 4 then is 5/6. That does in fact check out. That does in fact check out. There we go. Boom. That looks good. We got it. All right. Excellent. So, we're going to go ahead and take a brief break to pause there. I am going to charge my stylus, and we've got some more tricks and tips, if you will, some more theorems. This time coming up, we're going to be looking at how we can handle some variances, not just expectations, but what about combinations of variances? We'll see you in the next video.